Welcome back to the lectures on Introduction to Multi-Agent Systems. In the previous lecture, we discussed the eigenvector centrality measure. Now, the eigenvector centrality measure has a flaw that it generally is not applicable for several kinds of graph structures, in the sense that it does not reveal any meaningful information for certain graph structures, especially the acyclic ones. As a solution to that, in today's lecture, we'll discuss the CAT centrality measure, which is also a feedback-based centrality measure. So let's get started. Let us consider again a set of n agents and number of agents. As before, distributed over a network G whose adjacency matrix is given by A. We saw in the previous lecture that the eigenvector centrality sometimes does not work really well. As we saw in the previous lecture, eigenvector centrality does not reveal meaningful information in the case of some classes of directed acyclic networks. Does not, let's write it, always reveal. There are cases when it can reveal. For example, we saw that in the distributed averaging case, when we have a network which has a set of globally reachable nodes, such that the subgraph which forms the globally reachable nodes is obviously, it is already strongly connected, and it also should be aperiodic. In that case, eigenvector centrality can still reveal meaningful information and tell us which exactly are the central nodes. However, in general, for several acyclic networks which say have multiple sinks, eigenvector centrality will not reveal meaningful information. Meaning, we need to update the existing centrality algorithms such that we can have a measure, a centrality measure which can be applicable to a wider class of networks. The answer to this question, or the updated rule, is the rule of CAT's centrality. So what exactly is cat centrality. So the solution here is cat centrality. So what is cat centrality? Let's define it formally. For the ith node in the network, the cat centrality score is defined as follows. C cats, which is the cat centrality vector, and the ith entry of the vector is equal to alpha times summation of AJI C cats J plus 1, where alpha is equal to, or alpha is rather less than 1 by rho of A. Let us rearrange this expression a little bit more. This implies that C cats, okay, let's write the limits of the summation here, J going from 1 to N. C cats node I again is equal to alpha times summation J going from 1 to N AJI times C cats J plus alpha times the summation of only AJI, again J going from 1 to N. If we look closely here, suppose we did not have the second term. Let's put a cross over it. Then what do we have here? We have the eigenvector centrality. Similarly, if we remove the first part and only have the second part, then this gives us the degree centrality measure. Meaning, when we have both of the terms, let's write it. Suppose we look at both the terms now. Then cat centrality measure is actually a combination of the eigenvector centrality and degree centrality measures. We'll quickly answer the question now. Why did we choose alpha less than equal to 1 by the spectral radius of the matrix? And what exactly is alpha? Why do we need it? What are the kind of values it should have? Okay, let us try to understand that. Alpha is known as an attenuation factor, but what exactly does it attenuate? In order to understand that, we will do some more algebra with this expression that we have here and try to see if we can simplify it a bit more. Let's get started with that. Let us simplify the previous expression further. The Before we do that, let's first write the matrix representation of it. That will be easier for us. So let me erase this. The matrix representation. We have the vector C cats simply equal to alpha times A transpose, which appears in both the expressions here and here, is multiplied by, again, the vector C cats plus simply the all ones vector. This expression can be simplified to let us now try to do a simplification. So let us bring the C cats vector, let us collect it in one place, which will give us, write it here again, so it will be easier to follow. This is equal to I minus alpha A transpose times C cats is equal to alpha A transpose 1n. So how do we calculate C cats for using this? We will need to invert the matrix given here. But the question is this matrix invertible? Or rather, rephrasing the question a bit more, in what cases is this matrix invertible? Let us analyze that. For I minus alpha A transpose to be invertible, its spectrum must be must not be equal to 0. Right? And when can this be achieved? We must make sure that none of the eigenvalues of alpha times A transpose. So let's write it. It simply means that the eigenvalues of alpha A transpose must not be equal to 1, equal to unity. Let's say. In order to achieve this, we always choose alpha to be strictly less than, let's write it. We choose alpha strictly less than 1 by rho of A, which ensures that none of the eigenvalues can now be of the matrix alpha A transpose can now be equal to 1, which is what is the desired case. This is the reason why we have the condition of alpha being less than 1 by rho of A. Now coming back to this expression. So now we have chosen a suitable value of alpha. Let's write what is the suitable value. It is simply alpha being less than 1 by rho of A. So we do some more algebra with it. So we have this simplified expression. Now what more can we do with this? We simplify it a bit more. We now perform the inversion. So we have the expression C cats is equal to alpha minus 1 minus alpha A transpose, the inverse of this entire matrix times alpha A transpose 1n. where alpha is less than 1 by rho of A. If you, okay, what is this term equal to? You can apply a series expansion here and simply write that this is equal to alpha A transpose squared and so on times alpha A transpose 1n, meaning this entire matrix can now be rearranged as CATS is equal to alpha A transpose gets multiplied to each of the terms, and we have it is equal to the summation of alpha A transpose raised to the power k, where k goes from 1 to infinity. And the entire thing, the entire summation gets multiplied by 1n. So this is the expression of cat centrality. What does this expression mean? What does this signify? Let us see. If we open up the brackets, what we get here is that this is simply equal to let's write C cats equal to alpha A transpose plus alpha A transpose squared and so on and so forth, multiplied with the vector 1n. What does this mean? Remember that A transpose refers to all the walks in the matrix. And A transpose square refers to the walks of length 2. So this refers to walks of length 1. This refers to walks of length 2. And so on. Observe here, with every matrix term, we have another term alpha which is multiplied. When we are looking at walks of length 1, it's multiplied by alpha. When we are looking at walks of length 2, it is multiplied by alpha squared. And when we are looking at a walk of length k, it is multiplied by, we can rewrite the above expression as C cats is equal to the summation of k equals 1 to infinity and yet another summation of j, going from 1 to n, alpha raised to the power k times a raised to the power k and its j I and jif entry time. Okay. What does this now signify? Into 1n, because we have the vector entry. We can rewrite it if you want to do an node wise. So then we will stop right here. Okay. What does this mean? This means that walks of length k are attenuated by alpha raised to the power k. This implies walks of length k are attenuated by alpha raised to the power k, and the walks In this case, a walk of length k starts from some node j and ends at I, meaning it looks something like this. If this is a node j, this is node I, and this overall length is k. We are looking at all these parts. What does this imply? As the walks get longer, the attenuation becomes higher. The attenuation is more. Meaning, what cat centrality does is that it takes into account the relative importances not only of all of the in neighbors, but also every agent that has of every node that has a path to that particular node I. However, as the walks get longer, we give them little less important, and we prioritize walks which are shorter. So now we can summarize the key idea behind cat centrality through this process. Cat centrality computes the importance of a node by measuring the number of immediate neighbors, the number of in neighbors, say, and not only that, and also all the nodes which have a path, let's say node I, which have a path to node I. However, walks of longer lengths are penalized more. By using an attenuation term alpha. So let me summarize the results that we have so far. Excuse me. We started by saying the cat centrality is simply a combination of eigenvector centrality and degree centrality. Upon simplifying this expression, we arrive at this key formula. What does this formula say? By taking simply or by developing a centrality measure, which is nothing but a combination of the degree and eigenvector centrality, we have arrived at a measure which now allows us to give importance to every walk that exists to node I. In the process, we prioritize the walks which are shorter lengths. that means the nodes which are closer to the given node I, and we give less weightage to the walks which are long, meaning we give less weightage to the neighbors, not the neighbors, but the nodes which are farther away from the given node. So this is the key idea of cat centrality. So what should we do? How should we choose the term alpha? While we know that alpha should be less than 1 by rho of A, should we really make alpha very small? Should we make it very large? By large, we mean as close as possible to 1 by rho of A. How should we do? So let's discuss that. So what we are trying to answer is, what is a good choice of alpha? The answer is large values of alpha. Let's write it. Lead us to consider long walks. And this is the first point. The second point is that in this case, the cat centrality scores get closer to that of the eigenvector centrality. This is the first point. And what happens if we choose really smaller values of alpha? So then we are only prioritizing shorter walks, meaning obviously the results, the centrality scores that we get will be very close to the scores that we get by using in-degree centrality. Smaller values of alpha So the smaller the value of alpha, the larger is the attenuation. Smaller values of alpha make the results similar to degree centrality. By prioritizing the nodes which are closer. So these are the key ideas of CATS centrality. This is not the only variant of CATS centrality that is used in the literature. There are many variants. Just to give an example, we'll look at one more variant of CATS centrality. So let's write it. Another variant of CATS centrality. So this is very similar to the current form, but has yet another term appended to it. In this case, for the ith node, the CATS centrality score is given by C CATS I, meaning for the ith node, is equal to alpha times the summation AJI times C CATS of J, where the summation here goes from 1 to n, plus just another term beta. What do these two terms signify? So this is nothing but importance given to the neighbors and all the other nodes which have a walk 2i. What does the term beta mean? The term beta, on the other hand, represents the inherent importance that node I gives to itself. Meaning, irrespective of how it is connected to its neighbors, some of the neighbors could be important, some of them might not be important. It doesn't worry about that, or despite of all of it, it gives itself some constant importance, which doesn't change. So this is just another formulation. And in this formulation, if we set beta equals 1n, we get results which are similar to what we have from before, with just one added term. Let's do the computation here. Without loss of any generality, we consider beta equals 1n. Sorry, beta is a scalar because it is associated to the ith node. So it's a scalar. So we'll choose the value 1 here. Then Ccats is equal to alpha A transpose Ccats plus beta times 1n. But beta is equal to 1, so we can directly write now plus 1n. And again, as before, we choose alpha to be less than 1 by rho of A. Then further simplification of this, as before, leads to this expression. One minus alpha A transpose times Ccats is equal to 1n, and we know that 1 minus alpha A transpose is invertible, hence we have Ccats being equal to I minus alpha A transpose inverse into 1n, meaning we have I plus alpha A transpose plus alpha squared A transpose square, and so on and so forth. And all the terms here are multiplied by 1n. What do we observe here in this process? All of the walks to node I are attenuated. All the walks to node I are attenuated. However, inherent importance given to itself remains unattenuated. So this is yet another formulation in which the nodes give themselves some importance. Okay, with this, we summarize a discussion or conclude a discussion on cat centrality. In the next lecture, we'll look at yet another centrality measure, which is possibly by far the most popular centrality measure, known as PageRank centrality. Thank you.